This week we will be discussing or continue our discussion on evolution by natural selection, but we will very explicitly talk about the evolution of altruism. And in doing so, we have to recognize that there had been a push between about the 1930s and the 1970s towards embracing the concept of evolution of groups versus evolution of individuals. And this was really driven by this interest in explaining altruism. So we will distinguish this difference between individual and group selection, and then with Lecture 5 move into our discussion of reciprocal altruism. So almost immediately after Darwin published On the Origin of Species and put forth this theory of evolution by natural selection, there were attempts to discredit or detract from the strength of Darwin's theory. There were three main techniques that these objections took. One was to raise doubts about whether evolution had occurred at all, distracting attention from natural selection. One way this is done is through, pointing out the lack of key, let's say, quote unquote transition fossils, the quote unquote missing link, and really kind of shift that focus towards speciation and the fact that we cannot directly observe speciation occurring. The second was to acknowledge natural selection, but to minimize its significance by making it appear very weak in its effect. And so looking at things like phyletic evolution, again, at the this microevolution, but discounting whether it would be able to actually lead to speciation events. The third tactic was to replace the idea that natural selection acts on the individual with the notion that natural selection acts for the benefit of the group or species. And it is this third tactic where our discussion of altruism really comes into play. So when we define individual selection, we're talking about how the environment selects among the phenotypes at the individual level, that it is individuals' survival and or reproduction that is mediated through natural selection, and that the environment then sets the stage to either favor or disfavor traits. Group selection, by contrast, posits that certain traits seem to operate for the good of other individuals, and so this specifically deals with what we call altruistic behaviors. I'll explain that in just a moment. And that these traits are favored at the group level, even if they should be disfavored at the individual level. So we'll talk about, over the next few slides, we will talk about some specific examples of traits that appear to operate for the good of the group or the good of the species. But first, we'll define altruism. So the idea behind altruism is that individual behaviors that are dyadic in nature, that means one donor, one recipient, that in some cases the donor appears to pay a great cost in order to confer a great benefit to the recipient. So, the stereotypical kind of explanation or the example of altruism is like the man that runs into the burning building to save children that aren't even his. This idea that he would risk his life or even give up his life in order to save someone completely unrelated to him. And so this was the type of behavior that appeared to really require this group level of explanation. Darwin himself had stated that if any animal possessed a trait that was solely for the benefit of another animal, that his entire theory would collapse. And so people who were interested in really discounting Darwin's theory of evolution by natural selection kind of latched on to this this idea or this statement from Darwin that that it could lead to completely debunking his theory or the collapse of his theory, and thusly many explanations looked for these group level kind of descriptions or group level explanations for why these particular traits were favored. Despite Darwin's emphasis on individual competition and the differential reproduction of individuals by the 1930s, many biologists were looking at the function of traits in terms of species benefits. And there was a biologist, an evolutionary biologist by the name of Wynne Edwards, that brought this to light in 1962 with a book on group selection, and really looking across animal species for many cases, many situations where group selection may be the best explanation for behavior. So some of the questions that were posed by Wynne Edwards and other group selection theorists were, why do birds lay fewer eggs than they could? Particularly when they'll increase their overall reproduction if they lay more eggs. Well, at the group level, this laying fewer eggs than they could is explained by some kind of interest in population control. That it's better for the group or the species not to overtax their resources. And so in this context where there's going to be competition over finite resources needed for survival and reproduction, birds will give up some of their reproduction in order to help the species as a whole survive. In reality, we find in a lot of situations that the maximum potential reproductive output doesn't result in maximum fitness, and that instead there's some kind of what we call an interior optimum, whereby by limiting our reproduction, we're able to have more offspring survive to reproductive age themselves. And this is really what comes into play with birds not maximizing the number of eggs that they lay, in that they have to provide for the hatchlings, and by reducing overall egg output, they're able to maximize what we call fledgling success. That is, the number of their babies that reach this age that they're able to leave the nest and go out and take care of themselves. And so one of the ways that this is mediated is through the size of the chick at hatching. In general, the larger the chick, relative to its siblings at that point of hatching, the greater their survival. And so if by laying 4 eggs in a nest, 3 eggs in a nest, you can maximize that chick size, in stark contrast to the individual bird that might lay 5, 6, 7 eggs in the nest, then those 3 to 4 may have almost 100% survival. So, we have finite energy we can devote to reproduction. The more eggs that an individual female lays, the smaller each egg is going to be, the smaller each chick is going to be. And so it's this idea of the interior optimum. Why do animals give alarm calls? In many situations, it appears like there's a fitness cost to the donor of that particular behavior. So in this context of alarm calling, and we see prairie dogs and ground squirrels both engage in alarm calling, the individual that's doing the vocalization raises the likelihood that they are going to be picked off by predators. And so there is an actual survival cost that comes with giving this alarm call. When we examine this behavior more closely, we find that the individuals giving the alarm calls are often closely related to the animals that are around them and can receive the alarm calls. So it's not that they're sacrificing their lives or their own lives for the rest of the group to live, but rather that they're incorporating this kind of what we call coefficient of relatedness. We'll talk about that later on in this lecture. We'll talk about kin selection and this coefficient of relatedness as an explanation to explain some of these altruistic behaviors. And so the fact that they share genes because of close relation with other individuals in the group raises the likelihood that they'll be willing to bear a survival cost by giving this alarm call. Why do bees sting intruders even when it kills them? Well, bees are an interesting case because due to haplodiploid reproduction, sisters are actually more closely related to each other than they would be to their own offspring. And so they're related to each other at the 0.75 level, whereas if they gave up, or if they decided to directly reproduce, they'd only be related at the zero point 0.5 level, with the offspring having only half of their genes. So bees actually do better cooperatively protecting the queen, with whom they share such a high degree of relatedness. Why do animals commit infanticide? The idea that by committing infanticide, you're targeting weak members of the group, raising the overall likelihood that the group is going to remain strong. Well, in fact, infanticide is not indiscriminately practiced. We have infanticide at the case of other females, such as this female baboon that's carrying away this dead offspring, while also showing signs. If you look at the pinkness on her buttocks, she's showing that characteristic pregnancy sign. So by killing the offspring of competitors, really what she's doing is raising the likelihood that her offspring will be successful, kind of reducing competition for her offspring. When we see males commit infanticide, which, we can have, there's a type of monkey across the Indian subcontinent called langurs, and they're often viewed as sacred because there is a deity, Hanuman, who came to earth in monkey form, in Hindu and other kind of Eastern religions. And thusly, these monkeys are thought to, any one of them could house that kind of deific spirit, could be Hanuman coming to kind of test the people. Anyway, this particular species of monkey is single male, multi-female groups. And so when there is a takeover of a harem by another adult male, that adult male will kill any offspring that are still lactating, and also offspring born within about the next 5-6 months. The reason that the male engages in this behavior is because the offspring that are born within the next 5 to 6 months are not going to be his. They would be sired by the previous resident male, and by killing offspring that are still lactating, he's able to bring the females of that group back into estrus sooner. So he raises his own individual reproductive success by killing off competitors' offspring. And so according to Wynne Edwards, to be able to have group selection, you have to have groups that exist as isolated units. That is, there's not very much gene flow between groups. And so the idea here is that groups exist as isolated units in space, and some groups possess traits that make them more successful than others. And so some groups that do not possess these seemingly altruistic or group-selected traits will go extinct, and eventually then groups that do possess these altruistic traits will be able to take over the area previously inhabited by these groups. So we will have extinction of some groups without those favorable behaviors, and then the replacement of those groups that went extinct by groups that have the traits that promote group survival. George Williams went to graduate school as a student of Wynne Edwards and went into his graduate level research fully expecting to lend support and corroborate this idea of group selection. With his mathematical modeling, however, he ended up determining that group selection can't really occur, that all of these cases that his mentor was attributing to group selection were in fact better explained at the individual level. Generally, it's not a safe political move to come up with conclusions that completely invalidate your major advisor's life's work. So we will look at a hypothetical situation or a thought experiment that George Williams proposed. George Williams said to imagine that we have a city park that's inhabited by robins. There is only so much food to go around. If the robins reproduce too much, they will overexploit their food supply and cause their own destruction. So the group selection line of reasoning and what he fully expected to corroborate was that robins will exercise reproductive restraint to keep them in balance with their environment so as to preserve this particular group, so as to preserve the species. So the idea that we may limit reproduction in order to leave enough resources prevalent for everyone. We see this as an explanation or an appeal for modern human populations. There are some people who state that they favor zero population growth or even negative population growth, that they're not going to have offspring for the sole purpose of conserving resources and not overtaxing the climate, the environment, etc. But do we really expect even human idealists to really do it for these seemingly altruistic and species-oriented reasons, or do we expect people to have individual motivations? Well, for these robins, it's certainly individual level motivation. So imagine then that there are two variants, one that lowers its reproduction for the good of the group, the other that produces the maximum number that it can. In just that short time of one generation, there are going to be more individuals in that particular city park that possess the variant that maximizes reproduction. Because let's just hypothesize that those that exercise reproductive restraint have only 3 chicks per nest. Those that do not demonstrate reproductive restraint have 5 or 6 chicks per nest. In one generation time, if we go with 6 chicks per nest, they're going to be twice as many offspring that are born, that survive, that mature and breed in the next breeding season. They're going to be twice as many that are the selfish variant that are going to maximize their reproductive output. So these systems where group selection is proposed as the mechanism for these seemingly altruistic behaviors, they are really vulnerable to invasion by a single selfish organism. It doesn't take much to disrupt these populations that practice reproductive restraint, that seem to operate in balance with their ecosystem. And so, as George Williams worked through it, he came up with several implications. One is that all organisms will tend to be selfish. And really, when we look at individual level motivations, we are selfish. I mean, other animal species are selfish, trying to maximize their own and their offspring survival and reproduction. But really, humans are as well. I mean, we wouldn't have such a, let's say, economic divide and high levels of inequity if we weren't seemingly selfish, maximizing the resources that ourselves and our family have access to at the expense of others. Secondly, we're not going to find traits that are for the good of the group, species, or planet at the expense of the individual, because these systems are going to be incredibly vulnerable to takeover or invasion by selfish individuals. And organisms are not designed to maintain a population balance with the ecosystem. We don't try to balance out, as a variety of species, including humans, we don't try to balance out birth rates and death rates. Keep that in mind, because we'll talk about explanations for the demographic transition in week 7 that specifically purport that we balance out birth and death rates. And when those kinds of policies are implemented, they don't work. We are not, even as humans, a species that has evolved to lower our population pressures on our environments. We've got to highly incentivize those kinds of individual level payoffs to seemingly kind of being sensitive to environmental constraints. So organisms have evolved to really demonstrate that maximum reproductive output, not so much in number of babies that they have, but maximizing the number of babies that will survive to reproductive adulthood. And if we really were to see species that keep a balance with their ecosystem, we wouldn't have these population booms and crashes that are so prevalent. There's a really good example of one that has been observed across Canada, and that is a cycle between rabbits and lynx. Lynx, of course, being a wild felid, a wild cat. And so what we find is that in particularly wet years, when there's a boom in the production of grass, in other words, a lot of grass grows, we see rabbit populations boom. And so, of course, having an abundant supply of food leads to reproducing like rabbits, having really high reproductive output. When rabbits then have a boom year, in the next kind of breeding season following that boom year, we see a population explosion of lynx. And so when there's a lot of grass for rabbits to eat, rabbits reproduce at high levels. When there's a lot of rabbits to eat for the lynx, then lynx also reproduce at high levels. And so what happens after as this kind of cyclical increase goes on, well, as you have more rabbits that are prevalent, you've got more competition over access to grass, particularly if there's also yearly variation in rainfall totals. And so let's say a wet year with lots of grass is followed by a dry year. Well, you're going to have a lot of rabbits that starve to death if they're not eaten by lynx. Similarly, when the populations of rabbits crash, you're going to have a crash offset, however so slightly, in the lynx populations as well. And so what you get is this oscillation up and down and up and down. First the rabbits boom, then the next breeding season the lynx boom, then the rabbits crash, then the lynx crash. So if we were designed or evolved to keep this balance with our ecosystem, we wouldn't see that yearly or even seasonal variation. We would see just steady death rates and birth rates balancing out instead of having these population oscillations. And it's also been shown that group selection is mathematically improbable. In 1965, John Maynard Smith, who's really the father of modern game theory, showed that in order for group selection to work, groups must go extinct at a faster rate than migration outward occurs. In other words, we can't have very much gene flow between groups. We really have to have these groups existing as isolated populations. In reality, migration and dispersal are extremely common. So if there were a situation like this city park inhabited by robins and food supplies dwindle, the robins aren't just going to sit around and wait to go extinct. Right? Really, what the robins are going to do is relocate and find sites that have a greater abundance of food resources. So we see a lot of population dispersal and migration, both in and out of populations. And so we don't find a situation where we really have the prevalent features available for group selection even to emerge. This doesn't characterize real-world systems. And so this requires then a rejection of group selection. There are no natural phenomena that require a group level explanation. We find instead that individual level explanations are much more appropriate. There's a natural regulation of animal numbers that operates to prevent these kinds of mass extinctions that Wayne Edwards imagined. So, for example, migration, right? When food supplies start to dwindle, animals migrate, animals move, find new sources of food. So we don't see the need for this group level extinction or mass extermination. Actual data on breeding success shows that animals are reproducing as rapidly as conditions will allow, and without any concern over the possibility that the species will survive some future resource limitations. So we, both as humans and other species, we reproduce pretty much at the maximum level that we can, based on current conditions, not based on some hypothetical future condition. And so if there is any group selection at all, it's going to be a weak force, and it's only going to happen in these isolated circumstances where we get these very low migration rates. And so for each of the behaviors that group selection has been invoked for, we find that individual level explanations are much more appropriate.